Good morning to all. So today I am going to take class for the second year. I am going to continue the topic electricity and magnetism from the first unit, electrostatics. From this first unit, electrostatics, we are going to see about the Gauss law. Okay. So what is Gauss law and what are the things they are saying about the Gauss theorem? Okay. Okay. First, what is Gauss law? The total electric flux through any closed surface is equal to 1 by epsilon naught times the total charge enclosed by the surface. Means the closed surface has the electric flux at 1 by epsilon naught, and the total charge is represented as phi E is equal to Q by epsilon naught. Okay. So it was the first found by Gauss. Okay. So whereas epsilon naught is the permittivity of free space, okay, where epsilon naught is the permittivity of free space, free vacuum, electric intensity. Okay, here the electric intensity E is equal to 1 by 4 pi epsilon naught. So here we are going to take a closed surface where you can see. So you can see that. Wait a minute. You can see that the charge is at the center. Okay, so here the charge is being acting. Okay. So in the center, the charge is being acting. Okay. So then after plus q. Okay. Therefore, the radius is r vector. Okay. So the r vector is the radius between the center and the outer surface of the sphere. Okay. So here this E vector is equal to 1 by 4 pi epsilon naught. Since it is radius is covered 1 by 4 pi epsilon naught Q by R square. Okay, so we are taking a particular surface. Okay, so this surface, this is called ds. Okay, this surface is called as a ds. So this surface, so so E vector is equal to 1 by 4 pi epsilon naught Q R square into R cap. Okay, so here the R cap. Okay, so where here R cap is the unit vector. Okay, so here the R cap is the unit vector. Then after, if we see d phi E is equal to E vector into ds vector. Okay, so E vector into ds vector. So here we are going to simplify the term. D phi E is equal to E vector dot ds is split into n cap into ds. Okay, so n cap into ds. Okay, we are splitting the term ds vector into n cap into ds. Okay, so after differentiating phi E is equal to closed integral of s, sorry, closed surface integral of s, surface integral E vector into n cap into ds. Okay, so then after it is n cap into ds. Then after here, if you see phi E is equal to closed integral of s into lambda modulus of E cap, E vector into cos 0 into ds. Okay, so the n cap is represented as cos 0. Okay, so then after into ds. So therefore, phi E is equal to closed integral of s E into ds. Okay, so cos 0, we know that cos 0 is 1. Okay, so 1 into ds. Okay, so and after it is they are implying the term. Okay, so and after E we know that E is equal to kq by r square. Okay, so E is we know that E is equal to kq by r square. So therefore we are going to apply instead of E. So instead of E, sorry, here this instead of E, I'm going to apply this term. Okay, over here. Okay, this term over here. So then if you apply this term, Then phi e is equal to closed interval of s k into q by divided by r square into ds. Okay. Then after kq divided by r square into closed interval. Here this kq is taken outside. So this kq is taken outside. This taken outside, and after it is then it becomes as kq divided by r square into closed interval of s into ds. Okay. Then after we know that instead of k, I'm going to instead of k, I'm going to substitute the term. Then after sorry. So after, instead of k, I'm going to substitute the term 1 by 4 pi epsilon naught. So here this 1 by 4 pi epsilon naught is taken, and instead of k, I'm going to substitute 1 by 4 pi epsilon naught here. So k 1 by, so this r to get cancels, and then after, if I substitute instead of k, I 1 by 4 pi epsilon naught, the 4 pi cancel out, and then after the final equation becomes as q divided by epsilon naught. Okay, q divided by epsilon naught. Okay, so this is the final answer was Gauss explained clearly. Okay, so this q by epsilon naught is the closed interval surface. Okay, then after next, if you see, okay. Wait a minute. So, and after we are going to see about the electric field due to uniform charge sphere. Okay. So, electric field due to a uniform charge sphere. So, a spherically symmetric charge distribution means the charge density rho, okay, at the any point depends on the distance of the point from the center and not on the direction. Okay, so he's saying they are categorizing the thing into various segments. Okay, the case one. Okay, in the case one, when the point P lies outside the sphere. Okay, so here they are thinking when the point P lies outside the sphere, that is, they are taking a sphere, center is point is O, and the outer surface is marked as Q. Okay, so beyond the outer surface, there is a Gaussian surface. Okay, this Gaussian surface, there is a point P. Okay, so there is a point P. This. So this is a point P. Okay, here the point P. The point P. So the point P, the radius OP is the OP. There is a radius of OP. The OP is the distance between the spherical surface. Okay, so it's called as a radius. Okay, from the center of O. Okay, at the point of the sphere, the magnitude of the electric field E is same in the direction of the spherical surface. Okay, so the angle between the E and ds is 0. Okay, so therefore the angle is E and ds they are saying. Here the flux through the surface is closed integral of E into ds. So here, if you see here, there is closed integral of E into ds. That is equal to closed integral of E ds. Okay, instead of ds, we can write the term as 4 pi epsilon, 4 pi r square. Okay, so ds is the closed surface of the sphere. So instead of writing ds, we can write the term as 4 pi r square. And by Gaussian's law, we can say, apply that E into 4 pi r square is equal to, we know that Gaussian formula. Okay, Q by epsilon naught is the final output of the Gaussian formula. So we can take from that. And then E, we have to have the E in one side, and 4 pi r square should be transmitted to the other side, that is Q by 4 pi epsilon naught r square. Okay, so the resultant is here. Okay, so for this case 2, for the first case, the electric field at the external point due to uniform charge sphere is same as it's of the total concentrate. Okay, concentrate. It's equal to the total charge. Okay. So now after, when the point lies on the surface, okay, what will happen with the point lies on the surface? R is equal to capital R, E is equal to Q by 4 pi epsilon naught, Q by R square. Okay. Thereafter, when the point lies inside the sphere. Okay, so what happens if the point lies inside the sphere? See the diagram. So the Gaussian surface, first case we saw that the Gaussian surface is on the outermost orbit, outermost surface, and after we are going to imply this Gaussian surface inside. So what happens here? So thus the r is, that small r is being changed, and we are going to write the term as a total charge enclosed by the Gaussian surface Q1 is equal to 4 by 3 4 by 3 pi r cube rho into Q by 4 by 3 pi r cube is equal to, we are going to cancel out each other. Okay, 4 by 4, 4 by 3, 4 by 3 get cancelled, pi get cancels, and then after the remaining term is Q r cube into capital R cube. Okay. So then after, P is equal to charge density, that is charge per unit volume, Q by 4 by 3 pi r cube. The outward flux through the surface of the sphere R is closed integral of E into ds, that is E into 4 pi r square. Okay. Therefore, applying the Gaussian's law, that is E into 4 pi r square, here Q1 divided by epsilon naught is equal to Q by epsilon naught into R cube by R cube, capital R cube. So here, therefore, E is equal to Q by 4 pi epsilon naught small r divided by r cube. Okay, therefore, E is directly proportional to, at the center of the sphere, E is equal to 0. Okay, so here from the center of the sphere, the E is equal to 0. Okay, so the today class we ends. First we saw about the Gaussian's law, and then after about the electric field due to the uniform charge sphere. Okay. And after, thank you for listening in the class. Thank you. And we will see for the next class. We will see for next class.